All right, everybody. Thanks very much for coming today. I'm Thomas. I am one of the principal data scientists at a company called Quantum Black. We're a data science consultancy company owned by McKinsey, and I lead data science projects for clients in a multitude of industries, mainly across banking, pharmaceuticals, elite sports, and advanced industries. So that's kind of like the work that I do, but I'm not here to talk about that today. I'm here to talk a bit more about how to build models in a bit more of a principled way, because I've been at this company for a couple of years now, and like I said, it's like a consulting company, so you often do projects for 2 or 3 months for a new client each time, so you see a lot of things come and go, and you start to sort of notice patterns. So like one of the things that I noticed was that I was constantly running into the same kind of problems and writing the same kind of code around model selection and hyperparameter tuning. And I started to think about, okay, can I do this in a bit of a smarter way, you know? Because quite often I was just relying on the standard algorithm, standard like random search or manual grid search, which I think is still used by many data scientists, mainly for its simplicity, you know? It's just a very simple method to use and to explain to your non-technical stakeholders as well. But it just feels a bit dumb. So I started to think, I went on a bit of an effort to sort of understand better what's happening, and that's what I really want to talk to you about today. And what I really want to stress is, in the last couple of years, you can see that many researchers have spent a lot of effort into advancing sort of the state of the art in model selection and hyperparameter tuning. And this effort is not just academic. You will see that there are lots and lots of open source implementations of these algorithms available, which means that as a data science practitioner, it's actually very easy nowadays to start using these advanced methods in your project. So I'll highlight, so the goal of the talk is really to highlight a couple of approaches, and then I want to deep dive on a very recent approach that I found that looks very promising, and that also has open source implementations available so that you could instantly use them on your projects. But starting from the basics, right? Just want to make sure everybody's on the same starting point here. The problem we're dealing with is we have some kind of data set. Maybe it's tabular, maybe it's like a time series data set. And what we care about is building some kind of algorithm that performs well. And how we measure what is good performance, what is bad performance is usually through some performance metrics or some loss function, right? Which is dependent on your model type and a bunch of parameters of the model. And that performance metric is usually computed on some holdout set, so we make sure that the model can actually generalize out of sample. So this performance metric is dependent on your model and the parameters of your model. And what I want to stress here is it's not just the model necessarily that we can optimize here, right? You can see your model is just a function that takes data and outputs a prediction. So you can include your pre-processing steps, you can include your feature selection steps, your model selection steps. You can include that into one big sort of model algorithm function and try to optimize the parameters of that entire thing, which is what a lot of the AutoML solutions that are out there nowadays actually do. So these kind of optimization methods, many people use them just to tune the parameters of their single model, their XGBoost model, their IGBM model. But you can actually, if you want to, try to use these methods to optimize your entire end-to-end data science pipeline. So that's really what it is, right? Like we care about this function, or out of sample performance of our model, which is dependent on our data and on the parameters of our model pipeline. So as I'm sure you're all familiar with, the sort of go-to solution, at least the one that you learn in school, right, is let's just do some manual grid search over the hyperparameter space of my models, which is very easy to do and sounds like quite reasonable, but I'm sure you can all agree with me that this breaks down very quickly, especially in high dimensions, because the curse of dimensionality means that you're just trying to estimate the performance of the model from way too many configurations. So okay, what is your alternative here? And there's a paper I think by Bergström, who's a researcher that has done a lot of work in hyperparameter optimization methods, And in that paper, he argues, okay, for these high-dimensional optimization problems, you actually want to prefer random search over manual grid search because you have a better chance of like sort of exploring the high-dimensional hyperparameter space in that case. So fine, that's what happens, right? What I'm plotting here is like the performance function of a support vector machine as a function of only 2 parameters. So just a simplified sort of version of the hyperparameter optimization problem. So random sampling just randomly samples over this parameter space. But if you just look at this plot, you can already see, like, you know, if I sequentially start to sample points here, why, like, especially if I'm sort of in the top part of the figure where the performance is low. So blue means the performance is kind of low, and red means the performance is better, right? So higher is better in this particular case. You kind of feel that after you have sampled a couple of points in the blue space, that should give you some information, right? Like the fact that the performance is low in that subspace of the hyperparameter space should mean I should maybe start looking in other parts of the space. And this is kind of the thought that I had after sort of passing my probation period as a first-time data scientist. I was thinking, okay, I'm doing random search. I can sort of see that there are different regions in the hyperparameter space where in some regions my model performs better and in some it doesn't. But can I not use that information while I'm actually doing the optimization, right? And this is exactly the kind of stuff that advanced like hyperparameter optimization methods try to do. And that's what I want to talk about today. And before I go further, what I do want to stress is that whilst a lot of the methods that I will show are very, very neat, very intellectually satisfying for us data scientists, there's not always a need to go down this path, right? And it's exactly what I was describing earlier. If you are like actually in the case where you have either a low-dimensional hyperparameter space or you have an objective function that's very like cheap, computationally cheap to sample from, you may actually not need to resort to these kinds of approaches. Where this can really start to pay off is when either your parameter space is just very, very high dimensional, and a classical use case here would be some neural network type of approach, right, where you're really like tens of hyperparameters that you're looking at. Or you deal with a problem where getting a single realization of your performance metric is very expensive to compute. And again, a neural network can be a classical example. If it takes an hour to just get the out of sample AUC for your neural network for one sort of configuration, that might mean that you actually want to look at these kinds of methods, because then it becomes much more important where in the hyperparameter space you're going to sample from. So what's happening in the literature at the moment, right? So we have the field of like hyperparameter optimization, and in my head I usually sort of divide it in 2 different types of things that people look at the moment. So one thing that people focus on is making better search algorithms. And I've sort of divided it here in sort of 3 different approaches. I'm sure you can find many, many other ones, but I just want to sort of give you the high-level intuition here of what's happening and then dive a bit deeper on like one specific algorithm. So I've already discussed the random search and the grid search approach to this problem, right? So I don't think that needs like any more attention right now. But a very, very popular method that's still very competitive nowadays is what's called Bayesian optimization. I'll talk a bit more about it in a minute, but the idea here is that you're kind of building a model of this actual performance metric, and then you're going to use that model to sort of guide your search over the sort of the lost surface. And it's actually, so this is not a new idea. People have been doing this for a decade, if not longer already. So you'll see that there are many different implementations in the open source community out there. And people use, and I'm talking about making a model of the performance metric, right? And you can do that in different ways. So some people use Gaussian processes to do that. Other people use random forest-based models to do that. There's a lot of work in this space to like look at the probabilistic model, especially for Gaussian processes. People are spending a lot of time sort of trying to figure out what kernel functions work best for certain problems. So very active area of research. But just to give a couple of highlights, these frameworks are all 4 very mature implementations of Bayesian optimization algorithms. Some use Gaussian processes to do the optimization. So SMAC3 is an example of that one. Tune has also a Gaussian process-based implementation, but others focus more on the random forest-based implementation. Hyperopt is a prominent example in that space. I'll talk a little bit about why it may make sense to use a random forest-based approach over a Gaussian process-based approach a little bit later. Another approach that people do is what you could call a population-based approach, and this is much closer to what Marius was discussing in the previous talk. You know, this would be something like genetic programming. You're trying to sort of mutate the parameters of your model depending on what works well, what does not work well, and trying to see, and that way explore the parameter space in a slightly more efficient manner. What I'm sort of not showing in this diagram is the field of neural architecture search, which is quite recent and which really deals with like population-based methods specific to neural networks. But I'm taking a bit of a step back here and talking about more general methods that would work on any kind of like type of model and any kind of supervised learning problem. Prominent examples here are, again, Tune is a sort of very general framework, so they actually implement like many different types of optimization algorithms, so you'll see that appear throughout the list. But another one that you may be familiar with is a module called Teapot, and what they do is they basically try to solve this end-to-end machine learning pipeline problem, where they try to figure out, okay, what is the right pre-processing step to use, what is the right feature selection step to use, what is the right model to use, what are the right parameters of that model. So they really try to solve the whole problem by using a genetic programming approach. So that's one part of the equation. So people are trying to come up with more advanced search algorithms. Another thing that people are trying to do is they look at different variants of the original problem. And what that means is, and usually you split it up in two sort of things. You can split it up in multi-fidelity methods or what are called multi-objective methods. What does that really mean? A multi-fidelity method, what it tries to do is you take this original problem of trying to optimize your performance metric, but you're actually not going to try and solve that problem, but a related problem that is a bit easier to solve. An example of this would be, I'm going to train my neural network for only a certain number of epochs, and then after that number of epochs, I'm going to look at the out-of-sample performance and sort of see, is this model starting to look good or not? And if it looks really, really bad, I might already decide to bin it and look at a new configuration. Another example might be, we're just going to train our models on only a subsample of the data set instead, and use that as an indication of the performance on the full data set. So really the idea is you're using simpler problems to approximate this big problem that you care about. Again, there are many implementations about this. Hyperband is a relatively simple algorithm that falls into this bucket. I'll talk a bit more about that in a minute. And again, frameworks like Tune and Axis from Facebook also cover these kinds of methods. And finally, you would have these multi-objective methods. And what multi-objective methods do, they try to optimize for multiple different things at the same time. So it's not just looking at the performance metric. It might again look at cheaper to solve tasks like the multi-fidelity methods do, but it might also try to sort of take into account the time it takes to fit a model and sort of try to sort of find a good model that gives a nice trade-off between these two objectives. So as you can see, there are a lot of methods out there right now, and this is only part of the equation because I'm not even talking about the neural architecture search side of the equation or all the sort of automated machine learning platforms that are out there that are sold by the big tech companies at the moment. But you can see that all these things also have very mature open source implementations available. So I would highly recommend you to sort of, next time you deal with this problem, take a look at some of these implementations and see if you can use one of these things on your project, because you might be positively surprised. So that's sort of the current state of the world, right, in hyperparameter optimization. But what I want to do now is talk a bit more about a specific method that I recently encountered when I was looking into this thing. Because you have these methods, they fall into these different buckets, but what people now are trying to do is they're sort of realizing, okay, some of these methods work well in case A, and other methods work well in case B. So there's never like a silver bullet, like never an algorithm that always works, right? So what people are trying to do is sort of combine algorithms that fall into each of these buckets to sort of see if they can get the best of both worlds. And recently I came across a method that's called Bayesian optimization hyperband, or BOHB, that actually tries to take the ideas from Bayesian optimization and multi-fidelity learning, and specifically the hyperband algorithm, together to sort of get a very high-performant hyperparameter selection algorithm. So that's what I kind of want to focus on today. So this algorithm really consists of these two components, the Bayesian optimization component and the multi-fidelity component. So I'm going to spend a bit of time on that now. And the first component that I will explain is what's called the hyperband component. Are there any people that have heard about hyperbands by any chance? Some people. Okay, good. So then I'm very happy that I have this introduction here, because it doesn't look like that everybody knows about it. So what is hyperband? What is hyperband of an algorithm? So it's a banded-based algorithm that you can use to do hyperparameter selection, and it consists of one core component, one core subroutine, that's called successive halving. So what does successive halving do? Basically what you do is you say, I have a fixed computational budget. This can be a time. You can basically say, oh, I have 1 hour to run all my models. Or you can say, no, I have 1,000 epochs that I'm willing to sort of train my neural networks for. What's going to happen then is I have this budget. I then have what's called a reduction factor, which kind of means that the reduction factor, which in this particular example is I think set to 1/8, which means that at sort of 1/8 of that budget, I'm going to look at all my models and sort of see, okay, which ones are performing better and which ones are performing worse, and chuck off like 12.5% of the worst performing models for my data set. So let me repeat that again, because I jumped a bit ahead there. So what really happens is at the beginning, I'm going to randomly sample a number of configurations. I'm going to run that for a specific percentage of my total budget. So if we're talking about, so in this case, it could be 12.5% of my budget. Then I'm going to look at my 8 models in this particular case, and I'm going to say, okay, this model performs very well, this one also performs very well, but these ones actually don't perform very well. So what I'm going to do is I'm going to say the worst performing models, there's no chance that that this model is ever, or sorry, I'm flipping it around. This is actually worse, this is better, sorry. What I'm saying is that these models here, they're actually never going to get close to the performance of this model anymore. So there's no point in actually continuing to train these models. So let's just bin them and like focus only on training further the models that already start to look good. That's what successive halving basically does. So sequential, you have a total time budget, and at sequential points in time, you're sort of looking at the models you have run and binning a fraction of the models that are performing the worst. The problem with this method, and with any hyperparameter optimization method, is that they all suffer from what's called the exploitation versus exploration trade-off. And what that means in this particular case is with this method, with successive halving, I basically have a choice. At the beginning of that method, I can either say, let's just run a handful of configurations first for a very long time, and only then start to make a decision about which ones to continue with and which ones to not. Or I can make the decision to consider many different hyperparameter settings, but only for a very short amount of time, and then start binning the worst performing fraction of the models. And this is especially important if you have models that only start to differentiate in terms of performance after a high number of iterations, because then if that's the case, but you actually don't give your models a lot of time to train in the very beginning, you might make the wrong decisions. You might actually not make the right decisions, because the differences are only going to appear much later in your training procedure. So again, you have that kind of trade-off, and Hyperband is a method that tries to sort of solve for that by just taking the total computational budget and splitting it up in multiple pairs of, okay, this is the number of configurations I'm going to try for this particular budget. So you're going to have one combination which will try many configurations for a low number of iterations, and another combination that's going to try a low number of configurations for many iterations. To give that a bit more of a flavor, this is kind of what that would look like. So let's get everything here. Yeah, great. So kind of how this would work like Hyperband successor, multiple times is going to call this successive halving routine. So first time it's going to call it on this thing, where this is the number of hyperparameter settings that I'm going to look at. And this is the number of, let's say, epochs I'm going to run my models for. So in the beginning, it's going to call it for many configurations for only a low number of epochs, right? And then it's going to execute the successive halving method in that bracket. And what it does is then it has other pairs where gradually it sort of flips that behavior, so that at the very end, you're kind of arriving at a situation where you're only looking at a low number of configurations, but that you're definitely going to train for a high number of epochs. So you're kind of trying to hedge away this sort of exploitation versus exploration risk. Sorry? It's almost like a cross-validation over this choice of n of the number of configurations and the number of epochs or iterations that you train it. So yeah, you could definitely think about it in those terms. So this method, Hyperband itself, has been proposed, I think, in 2016 or 2017. So in academic terms, actually quite a recent method. And this is a plot that I dug up from a recent paper that also looked at the performance of Hyperband. And basically, they compare Hyperband against random search over a number of different data sets. And they found that it's very competitive against random search, especially if you have a short total computational budget. However, that kind of diminishes as you give your procedure a higher computational budget, because then the kind of random search is just able to kind of catch up on Hyperband. So a relatively straightforward algorithm. Many implementations exist, so I would already recommend you to look at that. But you can see, and that's kind of like the dissatisfying part of this, is that compared to random search for like long time budgets, you're actually not that competitive, right? 4x speedup means if I parallelize random search over 4 cores, then I'm basically there. So it's good progress, but we're not completely there yet. So the other component of the method that I wanted to talk about is what's called the Bayesian optimization component. And Bayesian optimization, that algorithm sort of consists of 3 steps. And those steps I've outlined here. So I've already mentioned that what Bayesian optimization does is it looks at your loss surface or a performance metric, however you want to call it, and it builds a model for that performance metric. That's what I call here my current belief of the performance metric. And you can do this with Gaussian processes, you can do this with random forest. There are many ways in which you can do this. But the idea is you have this probabilistic model that sort of tells you, that gives you an expectation of what the loss surface looks like. What you then do is, given that surface, you're going to try to use what's called a utility function or an acquisition function to sort of steer your search over that loss surface. So that utility function is going to tell you this particular space of the performance metric looks promising, go sample there. Or this particular space doesn't look promising, so let's just ignore that for the moment. What that kind of looks like could be like this, right? So what I'm showing you here is like 3 iterations of the Bayesian optimization procedure. The black solid line is what our current mean belief is of the objective function, and the dashed line is the actual objective. And this green function here is this utility function or acquisition function that I was about to mention. And you can already see that, again, Bayesian optimization, like any of these search methods, they suffer from this exploration versus exploitation trade-off. Because what you can do here is you kind of see that, if we're trying to maximize this function, you can see that here is actually the maximum of the thing. So you can see that the utility function in this point in time already says, okay, in that right corner, I think it's likely that we're going to find like an optimal for function there. So let's go sample there. Now we go sample there, and then suddenly this becomes the utility function. And what that's actually saying is, look, the utility function here is high, which is close to the points I've already sampled that look promising. So that means let's like try to exploit this good-looking region of the performance metric. But at the same time, you also see these regions that are more to the left, where you haven't sampled yet, and that's sort of kind of the exploration component, right? Because you don't want to overfit on that one area of the performance metrics that you have already sampled. So what these utility functions try to do is they always try to give you sort of this compromise between exploration of the space versus exploitation of the space. So like normally when I talk about Bayesian optimization, I would go into much more detail also about the Gaussian processes and stuff like that, but I think that I will leave to you for some bedtime reading perhaps. But I just wanted to give you a bit of an idea of what the algorithm actually does here, right? So coming back to this diagram, think about this Bayesian optimization procedure. It has three main components. We have a probabilistic model of our loss surface. We have a utility function that tells us this is a good region to look at, this is a bad region to look at, and we use that to propose a new configuration to actually compute the performance metric for, which is what happens at the end. And we then use that to update our current belief, and this is where the Bayesian component sort of comes into play, and then the procedure like repeats itself. So again, coming from the same paper as I pulled out the previous plot, what you then see is that compared to random search, you get very nice speed-ups given like long computational budget. So what it's saying is that Bayesian optimization is actually able to like explore that space much better in the long run, which is great, which is quite nice, right? So, but I found this very interesting when I saw this plot, because if you remember the Hyperband plot, which looks like this, you can sort of see that Hyperband seems to work very well for sort of low to medium computational time budgets, whereas Bayesian optimization, the behavior sort of seems to be exactly the opposite. So a very natural question is then can we sort of combine these two methods in a way that gives us like very consistent outperformance compared to a simple method like random search? And the answer seems to be yes, you actually can, which is what this Bayesian optimization Hyperband approach does. And the way that kind of works is it combines these two things in a sense that with your Hyperband procedure that uses successive halving, you're randomly sampling configurations. So what the authors of the BOHB method propose is to actually replace that random sampling component with a Bayesian optimization component so that you now get smarter suggestions in the Hyperband procedure to where to look at next. There are a couple of more tricks that they use. They don't have like a Bayesian optimization in each of those brackets. They have sort of a global Bayesian optimizer over the Hyperband procedure, and they do a couple of nifty tricks with the acquisition function. So I would recommend to like read the paper. I've linked it at the bottom. But the rough idea is basically to combine these two methods, and then you see that you get very consistent sort of outperformance against random search, which is quite nice. And the nice thing about this is these authors are actually like very well-known authors in the automated machine learning field. They're part of the Freiburg University. They have a good AutoML group there actually. And this method was used in their winning sort of entry in the latest automated machine learning competition at NeurIP. So it's definitely something that has also proven itself in practice. And they have made available an open source implementation of this. So I highly recommend you to give this a try. So that's really it. So what I want to sort of wrap up with, again, is my takeaway message. You know, many things have happened in the hyperparameter optimization space over the last couple of years. And many people have spent time in actually open sourcing the solutions they build. So there's really no excuse as a data scientist anymore to not look at these methods, not to at least consider them. They're never going to be a silver bullet. You know, there's no one true algorithm really, but there are definitely cases where this might pay off, and especially if you're thinking, and especially if you're in one of those two situations that I defined earlier, where you have a high-dimensional space or a function that is not computationally cheap to sample from. These methods may be useful for you. And there's a little bit of guidance here, right? So there are different sort of Bayesian optimization implementations, and I've sort of seen some of them work better in some cases than others. And especially, and one I think key thing that I wanted to highlight is if you have a configuration space that is very sort of that is either very large or is very conditional. And what I mean by conditional is if you have a search space that, for example, looks at a random forest model, an XGBoost model, and a linear model, each of those models will have more hyperparameters, but that's a conditional space, right? Because as soon as I choose one of the models, the rest, what happens in the rest of the hyperparameters of that, let's say I choose the random forest model, what happens to the hyperparameters of the XGBoost model and the linear model, that doesn't matter anymore because I'm not training one of those models actually. So there's actually a bit of structure in that parameter space, and if that's what's happening, then usually random forest-based Bayesian approaches seem to work quite nicely. That's really it. Thanks very much for listening, and yeah, thanks for your attention. Do you want this one?
Yeah. Against a tool, an algorithm that you know, and given, let's say, enough time,
Mm-hmm.
How do you personally fare in optimizing for a specific problem against any of the solutions you mentioned?
Cool. Thanks for the question. So I think it's a good question. It has depended a bit on the project that I looked at, and mainly it has depended on the additional requirements that were imposed on me in one of these in some of these projects, and that's specifically it has to do with more than just the model, right? Because what I'm trying to often do is I'm trying to optimize the feature selection approach, the imputation approach, and the modeling approach, and sometimes I deal with stakeholders where there are very stringent requirements on these features need to be in there. No, this imputation approach doesn't make sense. No, I need to have interpretability and all this kind of stuff. And usually when I have a lot of those boundary conditions, then I find that I fare much better. If I'm a bit more free and I only care about like predictive performance, then I find that these methods are actually quite useful. So for me, it's really like, what are the expectations of your model outside of like just having very high performance?
Thank you for the presentation. I just wanted to talk about, you did mention that we need high number of hyperparameters. Mm-hmm. Is there any threshold guide? So getting to like 20, 10, or that?
I don't have a threshold for you, but I would already say if you're trying to tune like 10 to 20 parameters, you might want to look at this, right? It depends a bit on whether these are continuous parameters or discrete parameters, but even if they're just binary parameters, with 10 parameters, you already think about 2 to the power 10 possible like configurations, right? So you can see that this space, it blows up very quickly as a function of the dimension. So like I think already with like 10, you could start looking at these kinds of methods. I think there's a question.
The Hyperband approach, how do you compare the model that has been trained by a lot of epoch and the model that has been trained by less epoch, larger configuration? Because for larger epoch, you always have a better model, and how do you compare the two?
Yeah, so the idea behind the method is that, sure, like often if you train the model for much longer, it'll have higher performance, but the assumption behind the method is that you can distinguish between models early on in their training procedure. That's the assumption, right? So if that assumption breaks down, which it can, especially if you think about like LightGBM, XGBoost type of models, where you usually get very good performance if you mess about with learning rate schedules and train it for many iterations. If that assumption doesn't hold, then Hyperband might break down, right? So it's all about this assumption that you can distinguish between models like early-ish in the training procedure.
Can you use this approach to optimize the hyperparameters for one particular type of algorithm? And if so, is it just as effective?
Can you repeat the question for me one more time?
So can you use this approach to optimize the hyperparameters one specific algorithm? Say, for instance, for some specific business problem, you wanted to use a specific machine learning algorithm. You wanted to use that approach to optimize the hyperparameters. That algorithm tests a lot of different models using that algorithm. You still use this approach?
I would say so, because all of what these methods assume is I have a function f, which is a function of a high-dimensional input space, and it returns a single number. Usually in machine learning, the performance of my model, right? But if it's like a business process, it could be like one way to think about it. Maybe I have a black box function in my business that given an allocation of, let's say like what is a good example? Like if I have some kind of distribution network and there's some kind of allocation of drivers to like depots or something like that, and I have a function that sort of tells me, okay, given an allocation, this is like, let's say, the efficiency of my system. I could use these methods to optimize that system as well, because all it assumes it's just I have a black box function f, I have inputs that I can optimize over, and a single valued outcome. So I think my answer would be yes to this question.
So would it be just as effective? Because if you're looking at a lot of different types of algorithms, like you're comparing linear models, tree-based models, and neural networks against each other, that's quite a large, diverse space. So when it's kind of trimming down the models that it's looking at, whereas as opposed to if you're looking specifically at one type of algorithm, the search space is smaller.
This would work back definitely, right? Like high-dimensional optimization is super difficult. So the more you can reduce the dimension of your problem by for example, throwing out a number of possible model types, you're making the life of your optimizer easier to sort of solve the problem. So yes, this would be a smart thing to do if you can. I think there's one there or there.
I'd like to know whether it's possible to mix transfer learning with
Yes.
because with transfer learning you may want to modify quantity later.
Yeah. So I think you could do this in the context of transfer learning for neural networks. I was just thinking about something. So there are two ways in which I can see transfer learning coming into play. One is with neural networks, right? And I think you could. I don't see why not. Again, I think all the framework needs is a black box function, right? And then when I'm retraining the last few layers in a net like I still have a black box function. So I think the answer would be yes to this. What people also have done is they've done meta learning in the context of Bayesian optimization. And what that means is they scrape like data sets from open data repositories. So let's say they scrape 1,000 data sets. Then they compute all kinds of meta features of that data set. So they would say, this is the number of samples in the data set. This is the number of features. This is the class imbalance. This is a classification problem. Stuff like that. And then they train a Bayesian optimizer over that data set. And the idea is that optimizer, given properties of your data set, can suggest to you good hyperparameter values. So that is kind of like a different flavor of transfer learning that can also be applied in this context. The idea is you're automating what the data scientist does, right? Because if you work a lot on Kaggle competitions or whatever, at some point you sort of know, okay, I have an XGBoost model, so I roughly need to set my learning rate at the beginning to this, and this parameter to that. So it sort of tries to abstract that knowledge into an algorithm.
In terms of transfer learning, let's say if you are using a very large model, let's say so you may want to create certain layer that specialize certain layers.
But I think it's exactly the same, because you're just looking at a performance metric, which is inputs and a single valued output. And if you're retraining only the top few layers in a neural network, you still have a performance function, right, that you're trying to optimize. So I think this still applies, actually.
Hi, thanks. That's all very interesting. I was curious why you honed in on Bayesian optimizer, and just kind of why you picked that. And I wondered if you explored past performance optimization.
Yeah, good question. So that would, I think that I in my head I put that part of the population-based like methods, right? No particular reason, to be honest. I think when I first started looking into it, Bayesian optimization was kind of the first thing that I stumbled into, and that kind of has like guided my search mainly. But I find this stuff very interesting as well. You can see that there are like competitive systems that are built on these like genetic type algorithms, right? Like driverless AI being like a good example. So again, like no particular reason, to be honest. And again, I want to stress there's not a single algorithm that always works best, right? Like the plot I show you looks very nice, but you need to understand that this comes from the authors of the method. So of course they're going to give you a plot that looks very nice. I'm sure it breaks down in some situations, but the evidence is still very nice and is motivation to actually try it yourself, I would say.